Right, thank you, Florin, and thank you everyone for coming along to see my talk. Hopefully this will be something that's mildly enlightening to you. I can't see you because I have notes on my screen, so yeah, if you have questions, please leave them to the end so I can see you and know that you're about to speak and those sorts of things. So this talk is called Fantastic Blocks and Where to Hide Them. My name is Christopher Neugebauer. This is the second talk in my series of talks about design patterns in Python that I've been giving over the last few years. I gave the first one at PyOhio a couple of years ago, and I gave the third at PyTexas last year. So if you saw my PyTexas talk, this is the talk that sort of led me to start thinking about the things I spoke about in my talk at PyTexas, which, as Florin said, you can find that in the Meetup notes on the Meetup site. Now, I'm going to skim over a bunch of unimportant details about the things I talk about in this talk. So if you do notice a detail that I skim over, it's not because I don't know about it. It's just because I don't think it's particularly important. So keep that in mind. So today's talk is about anonymous blocks. Now, blocks are a feature that was last seriously discussed in Python in 2005. That isn't being seriously discussed now and isn't likely to appear in Python anytime soon. So thank you for coming. I hope the talk is still useful to you though. So why am I talking about something that's not particularly relevant to programming in Python? So here's a quick summary of my biography. And if you'd ask me to summarize this biography, you'd note that firstly, I do a lot of things that are related to Python, but I don't do a whole lot of Python in my day job. Now, not writing Python means I spend a lot of time thinking about how to do things that I do, or how things that I do in Python are different from the language that I'm currently using. And the language that I'm currently using is Kotlin. In the past, that's been Java 8. I've also done a tiny bit of Swift in the last 6 or so years. And these languages are all object-oriented languages by default, but they're great examples of languages that have adopted functional style APIs where it makes sense to do so. That is to say, they encourage passing code around. Now, when I first used Python, it stood with Ruby as one of the two mainstream languages that encouraged this blend of functional style design alongside OO design. But these days, Python is less interested in this functional style programming, and that shift really started at the turn of this century. So starting in 2001, Python added a thing called the list comprehension. And this was the first of the features that it adopted that made functional programming less favored. It adopted things like generator expressions and generator functions. And by the time 2005 came around, Python had moved away from passing code around and towards providing syntax to accomplish similar results, which brings us to blocks. So first, let me explain what I mean when I'm talking about blocks. So Python has two ways to define executable bits of code. You can define a multi-line function. In Python, when you define a multi-line function, you must assign it to a name. You can also define a lambda, which may be anonymous or defined as an argument to a function, but it's only allowed to be one line long. Now, this becomes awkward when you want to pass a multi-line function as an argument to another function. So you have to define it, you have to give it a name, and then you have to call the function that accepts it as a parameter after you've defined it. This is quite roundabout compared with how other languages do it, especially if this function is only going to be used once as a parameter to another function. In Kotlin, for example, the multi-line example that I was talking about previously, this looks as natural as the single line example that you might write. So the conclusion here is that interfaces that expect blocks are not things that you would write in Python. They're not Pythonic. So today we're going to look at how Python's design choices have evolved parallel patterns to the block style patterns that other programming languages have. And then we're going to look at two cases where Python's design choices have kept Python from keeping up with languages that support blocks. And then we're going to show you how to contort Python to support these features in generally inappropriate ways. And we'll hopefully get some insight into how Python is keeping up with modern design patterns, and if Python is even able to keep up with those design patterns. So we're going to start with the case that informed the last discussion that core Python had around blocks. And this was in 2005, which was an interesting year in Python's history. It was the year after the two most important web frameworks of that decade were released. You're probably familiar with Django, which you'd know was Python's entry in that battle. And surprisingly for the time, the competitor didn't actually come from PHP, which is what everyone expected. It came from Ruby on Rails. And Ruby had a really interesting outlook on how to do programming, especially if you compared it with a language like Python. So Python has explicit loops and iterators, like with a for loop, for example, you explicitly declare that loop. Ruby strongly encourages developers to do things with blocks. The for each loop that's common in Python is normally implemented in Ruby by convention on container types. This is a philosophical difference between Python and Ruby, and either one of these two approaches is fine. But there was something that Ruby could do that Python couldn't. This is how you write to a file in Ruby. This is a function that's defined on files. It ensures that the file is safely opened before writing and safely closed before you move on. Now, if you're a Python developer, this approach is kind of weird, especially back when they were thinking about this, because the correct way to write to a file in Python was to do something like this. You have to correctly use a try finally block. Try finally blocks are quite awkward. You need to define a variable scope, a variable outside the scope where you start using it. So you're defining the file outside the scope. Then you have to remember to do the right things inside the finally block. Now, this approach to programming, it's kind of like putting a sign up that's telling people to please don't fall over in this place that might be slightly hazardous. Like the sign is there, it tells people what to do, to avoid it, but people are still going to probably fall over. It's actually worse than that. The design meant that it's easier to do the wrong thing than it was to do it properly. In this code, if writing fails, you may not actually clean up the file. You may forget to close it. And so it was that a bunch of PEPs were proposed in 2005. These ideas around file system operations, concurrency locks, a whole bunch of other things that looked like this behavior. And there was one PEP that got proposed in 2005 that looked something like this. It was proposed that it would be easy to write a with function that would take a block of code that would get run inside a context with the setup and the teardown performed correctly on either side. So this setup teardown pattern would be implemented correctly using this with function. And this PEP, as you may know now, wasn't adopted. Now, the reason why this particular PEP wasn't adopted was because it would lead to some general syntax that would create what the Python world would call a thunk, which is some code that's saved for execution later. Thunks are what we now know as anonymous blocks from other languages. Guido van Rossum thought that thunks created ambiguous expectations. He said, "I think I'd be slightly uncomfortable seeing a block and knowing whether it would be executed in the normal control flow." And so it was that we got the with statement. The with statement is a piece of syntax that keeps the main code in line within the calling context, but would then delegate the setup and the shutdown in a predictable way. And this differs from Ruby, where the setup and the teardown are part of the main control flow, but the block gets saved for execution somewhere in between that. It's by convention that the in-context block gets executed locally, but it's not a requirement. And this is a fairly standard pattern for Ruby. Ruby uses blocks in a certain way, and people make the language easy to use by handling blocks in that certain way. The expectation is that if you see a block, the control flow behavior will be obvious. Python's model instead opted to come up with a syntax approach that encodes the correct way to do things. So the with statement did away with that option that relied on convention, the try finally option, and replaced it with something that maintains predictable control flow. And this was understood at the time. Like the Zen of Python said, there should be one and preferably only one obvious way to do it. Now, not adopting blocks in 2005 proved interesting in another case. The year is 2006. The current version of Python is 2.4, and Python 2.4 has generators. Generators prove to be a great way of factoring out iteration patterns. Now, after a bit of playing around with generators, people realized that generators looked a lot like coroutines. Coroutines were a thing that people thought would be important in the 1970s. And they were so important that they made it into Donald Knuth's books. But by 2000, everyone realized that you could do concurrency with threads. And so manual concurrency models were thought to not be important. Python used threads for a while. But to placate the people who read Knuth, people realized generators, they look like coroutines. So Python 2.5 added a bit more syntax to generators so that you could actually write coroutines. Specifically, they added this syntax, which is called assign to yield. So now you can return some value to a calling context, pause this context until it's called on again, and then receive values back from the calling context. Now, this sort of pattern is the building block of non-blocking I/O, and it does this in a way where the control flow is linear and easy to understand. But Python coroutines were still awkward to use in practice. They relied on concepts that were based on iteration, and they made sense with generators because generators were written for iteration, but they didn't make sense with concurrency. This idea of next and stop iteration sort of doesn't make much sense in the context of a coroutine. And in 2008, when Dave Beasley gave a tutorial on generators at PyCon US, he concluded, quite rightly, that most programmers don't really understand generators. So in 2008, we had this great syntactic and structural approach to do non-blocking I/O, but was a bit weird and nobody understood how to use it. In 2009, on the other hand, something remarkable happened in the JavaScript world. That thing was the invention of a thing called Node.js. Now, Node.js, at least as originally planned, implemented basically everything using blocks that would represent callbacks that would get run whenever an otherwise blocking function got finished. Now, this solved the sort of concurrency issues that a lot of web programmers actually faced, but they were solving with threads at the time. And it turned out that doing things asynchronously without threads was actually very, very, very fast in comparison with those threads that people were used to. The problem with using blocks in this case is that handling sequential operations tends to get really unwieldy. So this bit here inside the braces is a callback block, and that callback block also needs another callback block, which is nested inside the first callback block, which is nested inside the calling context. And we can all agree as Pythonistas, this approach to doing things looks really, really, really ugly. But on the other hand, people didn't understand how coroutines worked, so they just used blocks anyway. It wasn't until 2014 that Python started seriously considering coroutines as a way to do non-blocking I/O. Python 3.4 added a thing called async I/O, which is a full suite of async I/O routines based around those coroutines that people thought were impossible to understand 6 years prior, and they still use this weird generator syntax. Python 3.5, once async I/O was released, added some syntax to make it clear that there was async stuff going on. It's really easy to understand this compared with generators. Basically, if a function calls an async function, it must be async itself, and await can only be called on async functions. This syntax worked really well. Async I/O was reasonably good, and the Python 3.4 approach was so good that JavaScript immediately adopted the coroutine approach, and it picked up the async await syntax at almost exactly the moment that Python proposed it. So by not having blocks, Python rekindled this 35-year-old thing that nobody used anymore called coroutines, and we actually got an intelligible syntax for cooperative multitasking. But it took 5 years for people to start taking it seriously. We missed this syntax advantage that we had before Node.js even existed because the libraries weren't there, because people weren't dealing with coroutines. But we did end up helping JavaScript find a better way to express non-blocking I/O than blocks, and Node.js got better. Yay. So let's take some stock now. We've learned that Python values linear control flow, and Python doesn't have blocks because they allow for control flow to become nonlinear. We've also learned that Pythonic ideas tend to migrate out of Python. So this is how I classify Python pre-2010. Python found better patterns because it didn't have blocks. But what's happened as languages with blocks have started growing over the last 10 years? We're going to start by looking at how a pattern from the 1990s has developed. This book is the Gang of Four book on design patterns. It's from the 1990s. It introduced a whole pile of design patterns that made it easier to structure software within the feature set of the object-oriented languages of the time. These languages were C++ and Java for the most part. One such pattern is called the builder pattern. The builder pattern is a way to use object orientation to construct free-form hierarchical data structures. The builder pattern is common in Java, but the builder pattern in Java is terribly misused. It's favored as a way to work around Java's lack of optional parameters in functions. In essence, most people started using builders in Java for building single objects rather than hierarchies. Of course, Python has optional arguments, and what this ends up meaning is that people who code Python, they tend to look unfavorably upon builders as something that's useful. Brandon Rhodes has a Python design patterns book that talks about the builder in its original context. He shows examples from the sciences and from the standard library that use builders. The element tree library from the standard library and matplotlib are both examples of libraries that present a builder interface. Now, here's an example of using a builder library to build up an HTML document. This is a simplified version of element tree, basically. HTML tags are nested data structures, so you can use nested builders to build each subnode of the tree. You build the subnodes up, and then you call build on everything that gets you the actual object that you've been defining with your builder. So that's the interesting thing about builders. Builders themselves are not particularly important at all. They are an intermediary towards getting the data structure that you want. What you actually care about is to have a declarative way of building up your data structures. So if you have a function like this that takes a tag name and a block, say you have some way of defining blocks, you can create the builder, you would run a block that accepts that builder, and then you would build the builder after you ran the block that accepted the builder. Basically, you're abstracting away the setup and teardown of the builder, leaving the declaration of the structure to the programmer. And this is what that looks like in Kotlin. It looks like a description of a data structure. This sort of thing would feel really at home in Python because in Python, we already have list and dictionary literals. We can use our language to describe certain data structures. What these implicit builders give us is a way to describe any data structure in code. So it'd be very nice if we could do this in Python. So can we do that? Okay, so what we're going to do is we're going to make a builder class which takes a tag type as a string and has a list of child elements. And then we're going to write a build method because this is a builder, of course. The builder produces some text. And then we're going to add a way to add some text to one of those tags. Now, we're going to optimistically add a method that takes a block and uses that to build a child tag. Now, obviously, there is no support for blocks in Python, so there is no way this would work. And we're going to add a caller function that encapsulates all of this so we never have to explicitly build up one of those builders. So we have these two APIs that require a block. How would this actually work in Python? Well, it turns out that the signature for a function that accepts a block is the same as the syntax for decorators. And that means that you can define an HTML document like this. Each tag is built up with a nested function. And this piece of Python code produces that HTML document. Now, what's weird is where that HTML document gets stored. What we thought was a function definition is actually defining an HTML string. Using that markup decorator, using that decorator is what causes the builder to get invoked. And a decorator stores whatever the decorator function returns under the name of the function that you're decorating. So we have working implicit builders. We can define our data structures in code using real Python syntax. But is this good Python? Well, let's ask the Zen of Python because that tells us everything we want to know about Python. It says, if the implementation is hard to explain, it's a bad idea. Now, this is obviously hard to explain. We're hijacking the def keyword to store things that aren't functions. Nobody would understand what's going on here. But there's a bigger point here. If Python is in favor of using syntax to indicate the shape of control flow, which is what Guido suggested in 2005 when rejecting blocks, well, you have to ask, is the use of decorators at all Pythonic? Because we've just seen that applying a decorator to a function doesn't even guarantee you that you'll have a function after the definition has completed. And the answer to me is that decorators work because there is a strong convention around their use. But as we've seen from Python's development over the years, it isn't good practice to rely on convention. So we're going to finish with a discussion of tools for error handling, because errors are a fact of writing programs. Now, it's fair enough to assume that errors don't have to be catastrophic. Errors can be things that are transient, like recoverable network errors. But errors can also be halt and catch fire sort of errors. And Python only really gives us tools for handling the catastrophic variety of errors. So let's say we have an application that takes a request to create a user. That application is going to call an internal API to create that user and is then going to return a success or failure response back via the API. So the internals look like this. And if everything is successful, this code is great. But we're not expecting any errors to happen. Here it is once you handle the error. The code starts looking really complicated. You have to sandwich the error handling in between the success case. And so the error path is actually easier to read than following the happy path. This idea where you separate the first part from the second part is called poor locality. This is where two bits of related code live visually far apart within your source. Now, what if we have to do something with our response after it's created, regardless of whether it's a success or an error? You'd rearrange the code like this, and the code locality is actually improved by doing this. But what if this bit here causes an error? So there's two lines of code inside that try block. It's now hard for the except block to know which line of the try block is responsible for the exception. So what you can do is you can abstract away the bit that causes the error and then abstract away the functions that create the responses. But now you have even worse code locality. So instead, we could fall back to using old-fashioned if statements. But this is ugly because we're relying on defining the same variable inside both branches of the if statement, and then we're testing that value one level up. And it's relying on convention. So perhaps there's a structured way to do this instead. The functional programming world has a thing called an either type. Now, an either type is a type that can hold either of two types of values. For example, a success type and an error type. If you use Python's type hints, this is called a union type in Python type hinting language. Now, once you have an either type, you can perform an operation called fold. Fold takes a success handler and a failure handler. It runs the one that's applicable, and then it returns a common value type. So if you recall, our unstructured Python example looks like this. A structured version in Kotlin looks like this. We give the happy and the unhappy paths equal locality, and we define that response variable just once. But that's an application of convention again, and Python frowns upon convention. For something to be truly Pythonic, we'd rather see some explicit syntax for it because syntax is what guides us to understanding control flow. And the functional programming world has a thing for this as well. It's called pattern matching. Pattern matching is a structured way of using types to determine which code gets run. And in Kotlin, it looks like this. You use a when statement and you provide a block for each type that you want to handle. Each block returns a value which gets assigned to a common assignment statement. So can we do pattern matching in Python? Well, that would depend on us thinking whether matching on types is Pythonic. And well, we know in Python that types are always meant to be very optional. Background is things that you should never rely on, never expect to be there, definitely. But what if all of your return types were to inherit from base exception? Well, you can throw your return type, and then the except statements are all pattern matching operations. So Python actually has pattern matching built in, provided your type hierarchy inherits from base exception. But that has the same problem as the if statement. We're still redefining variables everywhere, and that isn't very neat, so syntax doesn't work. So let's fall back on convention. Let's try and implement fold. So we're going to define a folder class with a way to register some functions, and of course a fold function in there as well. And then suddenly you can call fold like this. You define a success type, a failure type, failure handler, and well, what if you wrap all of that in an outer function? And what if you invoke that outer function using a decorator? Well, that means we've implemented fold using decorators and implicit builders. And at this point, I found myself a bit confused. Because in my research, I learned that Python is in favor of using syntax to indicate the shape of control flow. But if that's the case, well, you can define a function with a couple of callable parameters and non-callable parameters, and then you can write this code, and it stores the result of calling that function that you define, which is to say that Python gives you a syntax that lets you call a function just by defining a function. So decorators not only rely on convention to be used correctly, they actually let you completely invert the expectations of control flow that is set by the rest of Python's syntax. So in Python, with normal syntactic features, you can call functions by simply defining them. So I apologize profusely for that. So before I conclude, some observations. Some Python constructs are much, much nicer than blocks. Some of the important design patterns that have come up since then don't have good analogs in Python, but we see that Python already supports throwaway blocks through the use of decorators, so maybe we should just find some better syntax for dealing with anonymous functions. Thank you to Steve Dower and Nick Coughlin. They helped me develop some original ideas for this talk, make sure that the implementations weren't entirely terrible. Thank you all for coming along. I hope you found that interesting, and I'm now happy to take some questions.
Were you planning on going into hiding after giving this talk, Chris? Because
I've given a couple of times, and I was not hunted down for sport afterwards. And I've since given a sequel to the talk where you can see where the refined version of some of these ideas, which is in the talk I gave at PyTexas.
Okay. I mean, yeah, this is like stuff that's really cool, and if anybody ever actually did a PR at work with those last bits in it, my head would explode. So
see, this is where I refer back to the Zen of Python, which is it has that great line which says, if an implementation is hard to explain, it's probably a bad idea. And I find that just falling back on that line is a great way to push back on code that can be problematic. You know, you can ask your colleague to explain what they're doing, and once it turns out it takes them an entire talk with a week's worth of preparation to explain how it works, that's when you know it's more effective to just write the code in the obvious way.
Yeah.
So,
if you get somebody to draw a diagram and it's a big spaghetti mess, if you can work it out and untangle it on the screen or on the whiteboard, in a lot of cases, the paradigm shift that it takes to do that is the paradigm shift that your code needs to make your code a whole lot better too. So I find that an effective way to do refactoring.
So Patrick asks a question, not familiar with the details, but there are some ideas around adding pattern matching to Python in PEPs recently. Can I describe real quick how that related to your ideas here? So I wrote this talk in 2019, which was, when I wrote it, I think was the very week that that PEP about pattern matching got proposed, and it's still in a draft state. At the moment, I would be surprised if that pattern matching thing got accepted, but I also am not the core Python team. I don't speak for them. I don't know what's necessarily going to happen there. I would say there'd be more incentive to use types, and there would probably be some syntax that lets you do some of the things I spoke about in my bit about pattern matching in a way that's a bit more Pythonic. You wouldn't necessarily need to start looking at implementing fold, for example. You'd be able to use pattern matching to do that error handling. And like, as somebody who spends a lot of day job time not writing Python, instead writing Kotlin, which is a language that has pattern matching, I find that pattern matching is a much more natural way to deal with routine errors than exception handling ever is. So it's something I'd like to see in Python if they can make it less ugly, I guess.
I have a question, and actually draws from possibly your conclusion at the end. Why do you need blocks anyway? Because Python has better mechanisms. This is at least what I understood from your talk.
Yeah. So I think. Oh yeah. Do you want me to explain that, or?
Please go ahead, explain this. Maybe I misunderstood something, but okay. Then I will ask you a question.
Yeah, I think there's two parts. I think there are a bunch of cases where Python came up with solutions that are better than the alternatives that were being used with blocks at the time, and there are patterns that have come around since since 2010. I think that don't have good analogs in Python at the moment, and maybe blocks are the way to solve it. Maybe they aren't. Like introducing pattern matching, for example, would be better than blocks, I think, but I still don't have a good example of, or a good idea of how you'd get these structured implicit builders that I spoke about in the third part of the talk.
Okay, so I got some of what you're saying, but then again, I'll go back to the absolute beginning. The way you explain blocks is something like a lambda function with multiple lines in it. But even in the example that you showed, you actually assign a lambda function to something. Basically, you name it. Think about it. Eventually, why is the name that important? In Python, the function is going to be read on the way the minute you define it. And it will have a name, but then later we assign it to whatever you want. What's the problem then?
So I think in the example I showed, I assigned it to a name for no particularly good reason, but with a lambda, you can provide it directly as an argument to a function. I think the question that I have about like the utility of multi-line blocks here is that if you want to define something that takes two multi-line blocks, there's not a particularly good way to do that in Python. You can argue for something that takes one multi-line block, defining a function and then throwing it away immediately after you've defined it. That might be okay, but I find like your code locality gets pretty bad once you start dealing with multiple block parameters, and functions like patterns like fold, for example, which take two blocks, is quite hard to define in Python in a way that's natural. So yeah, the name of a function sort of doesn't need to be important. You could name a function and then delete it immediately afterwards, but but I find like the style of code can get worse as you start dealing with more than one.
And specifically for the folds, when you define the function, does it define one or the other with like in an if statement with multiple logical operators? Like it executes only the one that's needed, or does it?
Exactly. Yeah.
Okay. So this is the thing that you want. You want to be able to define a function which has elements that will change during execution according to what's happening at this moment of definition, or according to runtime?
At runtime.
So you want the function to be defined on the fly on runtime, but only the part that you want.
That's one way to look at it. Yeah.
Okay, this requires some thought. Yeah. Thank you.
Anyone else?
Yeah, lambdas are pretty amazing things for it can be used so many different purposes.
Oh, does anyone else have a question? Cool. I'm going to disappear for a bit because it's coming up on dinner time here in California. I may or may not be back for a discussion at the end of the session. If you do want to talk to me, you can find me on Twitter at ChrisJRN. You can also email me chrisjrn@chrisjrn.com. Cool.
And Chris, real quick, Chris, I appreciate you introducing some concepts I've used a with in my code, and now I better understand it. So thank you very much.
My pleasure. Hey, see you all next time, hopefully in person at either one of your meetups or at a PyTexas one of these years, because I miss hanging out with all you Pythonistas. All right.
Thanks.